We need to talk about that annual ritual. You know the one I mean.
Oh, I do.
The leaves start to change color, the pharmacy signs all go up, and you go in to roll up your sleeve for the flu shot. You do the responsible thing. But then, fast forward 2 months, you're on the couch, shivering, surrounded by tissues, just wondering, why did I even bother?
It's a frustration that I think everyone listening has probably felt.
Hmm.
And it's not just in your head. It's a statistically validated frustration. You're essentially betting on whether a group of scientists months in advance successfully predicted the future of, well, viral evolution.
Right, and hearing, oh, it was a mismatch year does not make you feel any better when you have a fever of 102. But
Yeah.
that is exactly why I wanted to pull this specific deep dive together. We're not just looking at the problem, we are looking at a paper from NPJ Vaccines published back in 2019 that proposes a way to stop gambling.
We're looking at a vaccine candidate called OVX836.
It sounds a bit like a license plate.
It does. Or maybe a droid from Star Wars. But the technology behind it is genuinely a fundamental shift in how we think about immunology.
The headline promise here is really what hooked me. We're talking about moving from chasing the virus's disguise to targeting its heart.
That's a poetic way to put it, but it's scientifically pretty accurate. The promise is a vaccine that works regardless of the specific strain that's circulating that year.
A universal component.
Exactly. But to really appreciate the solution, we have to understand why the current system fails so often. Because I think most people just assume if the flu shot fails, well, it's just bad luck.
But the source material suggests the failure is actually built into the design of our current vaccines.
It is. I mean, think about what we're currently injecting. Standard flu shots, we call them inactivated influenza vaccines, or I5Es, they rely almost entirely on creating antibodies. And those antibodies are trained to hunt for surface proteins, specifically one called hemagglutinin.
And that's the H in H1N1 or H3N2.
That's the one. Hemagglutinin is like the coat the virus wears. So the vaccine takes a snapshot of that coat, hands it to your immune system, and says, attack anything wearing this jacket. The problem is, the flu virus is sloppy when it replicates. It mutates constantly. It changes the jacket.
This is antigenic drift.
Right. So the virus changes its outfit, and suddenly the immune system's wanted poster just doesn't match the suspect anymore.
And the data on this is, well, it's pretty stark. I was looking at that meta-analysis in our notes. It covered flu seasons from 2004 all the way to 2015.
The numbers are sobering. Against the H3N2 strain, vaccine efficacy averaged out to only about 33%.
33%. So you go through all the trouble of getting the shot, and you're still failing 2 times out of 3.
In some years, yeah. I mean, take the 2014-2015 season in the Northern Hemisphere. That was a particularly bad year. There was this significant drift mutation in the H3 strain, and the vaccine efficacy. It dropped to an estimated 23%.
23. That effectively means the vaccine did almost nothing for the vast majority of people against that specific strain.
Correct. Because the antibodies didn't recognize the new coat, we were chasing a ghost.
Yeah.
And that is the trap of the current technology. As long as we target the surface, we are completely at the mercy of the virus's ability to change.
So enter OVX836. How does this candidate flip the script on all that?
Well, by ignoring the surface entirely, this new candidate targets the nucleoprotein, or NP.
Okay, nucleoprotein. So if hemagglutinin is the coat, what is the nucleoprotein?
It's the internal architecture. It's on the inside of the virus. Biologically, this is crucial because while the surface coat has to change to evade antibodies, the internal machinery, the nucleoprotein, it has to stay the same to function. It's what we call highly conserved.
And when you say highly conserved, are we talking about just a slight resemblance, or is it a near match?
It's a near match. The research highlights that even really divergent flu strains differ by less than 11% in their nucleoprotein. And within influenza A strains specifically, you're looking at greater than 95% homology.
So basically, if you look at the guts of the virus, an H1N1 from, say, 1930 looks almost identical to an H3N2 from today.
That's it, exactly. So if you can train the immune system to spot the nucleoprotein, you're effectively training it to spot almost every version of the flu that exists.
That sounds perfect. So why haven't we been doing this for 40 years? Why are we still messing around with the surface proteins?
Because the immune system isn't easily tricked. It focuses on the surface of invaders because that's what it encounters first. Internal proteins like NP are naturally what we call weak immunogens.
It's too boring for the immune system to notice.
Essentially, yes. If you inject plain nucleoprotein, it doesn't trigger a massive alarm. It just doesn't wake up the defenses enough to build a lasting memory. Plus, there's a mechanical problem. Antibodies are like bouncers. They stand outside the cell and block the virus from getting in. But since NP is inside the virus, antibodies can't really reach it effectively.
Okay, so if we're not using antibodies, the bouncers, what is OVX836 trying to activate?
Cellular immunity, specifically T-cells.
Right, we hear about T-cells a lot, but usually it's in the context of, oh, I have T-cells, so I'm safe. But functionally, how are they different from antibodies?
Okay, so if antibodies are the bouncers at the door, T-cells are the internal security team, the cleanup crew.
Ah.
They can't necessarily stop the virus from getting in the front door, but once a cell is infected, T-cells recognize the distress signal, and they destroy that infected cell before the virus can replicate and spread.
So one blocks infection, the other clears an infection.
Precisely. And we know this mechanism works. The paper points to the 1957 H2N2 pandemic. There was this fascinating pattern where adults who'd been exposed to older flu strains decades before had much better survival rates than children.
Even though the 1957 flu was a totally new strain.
The surface was new, yes. But the theory is that the adults had this pre-existing T-cell memory of those internal proteins, the nucleoproteins, from previous infections. Their bodies recognized the guts of the virus, even if the coat was brand new.
Okay, so we know T-cells work, we know nucleoprotein is the right target, but you said it's a weak immunogen. It doesn't get the attention of the immune system. How do the researchers behind OVX836 actually solve that problem?
This is the engineering breakthrough, and it's really all about structural biology. They didn't just take the nucleoprotein, they rebuilt it. They used recombinant protein engineering to fuse the nucleoprotein to a specific tail. It's called OVX313.
OVX313, is that like a chemical additive, an adjuvant or something?
No, it's actually part of the protein structure itself. It's an oligomerization domain.
Okay, break that down for us. Oligomerization domain.
It's a piece of genetic code that basically forces proteins to bind to each other in a very specific pattern. In this case, it forces 7 nucleoproteins to snap together into a ring, a heptamer.
A heptamer. So instead of one protein just floating alone, you have a cluster of 7.
Exactly. A stable 7-unit bundle. The researchers sometimes call it a spider structure because of how it looks. And it turns out geometry matters immensely to the immune system.
Why? Why does the number 7 or a cluster make any difference to a cell?
It's all about visibility to the dendritic cells. These are the scouts of the immune system. Their job is to prowl around, grab foreign debris, eat it, and then run back to present it to the T-cells. The study showed that dendritic cells internalize this heptamer structure much, much more efficiently than they did the single protein.
It's the difference between a crumb on the floor and a whole slice of cake. The scout is going to pick up the big chunk.
That is a perfect analogy. The spider structure is just physically harder to ignore. And because the scouts took up more of it, they were able to scream louder, so to speak, to the T-cells. The data showed significantly stronger CD4 plus and CD8 plus T-cell activation compared to the standard nucleoprotein.
So they use geometry to solve the boring protein problem. That's incredibly cool.
It really is. It's hacking the immune system's perception.
So let's get to the results. They tested this in mice. What happened when they actually exposed them to the flu?
The immune response was fascinating,
Yeah.
particularly regarding where the response happened. The vaccine didn't just create memory T-cells floating around in the blood. It created tissue-resident memory T-cells, specifically in the lung parenchyma.
Parenchyma. That refers to the actual functional tissue of the organ, right? Not just the blood vessels running through it.
Correct. This is boots on the ground right at the border. I mean, influenza is a respiratory virus. It attacks the lungs. If your T-cells are just in the blood, they have to be recruited, exit the blood vessel, migrate to the infection site. That all takes time the virus uses to replicate. OVX836 stationed the guards right in the lung tissue, ready to deploy immediately.
And speed is everything when a virus is replicating exponentially. So did they survive?
They performed lethal challenge tests. This is really the gold standard. They immunized the mice and then hit them with lethal doses of flu. First, they tested it against H1N1, the same strain the vaccine was based on. In the control group, the mice that got a placebo survival was 10%. Or less. Most of them died. In the OVX836 group, 90 to 100% survival.
Okay, but that's the homologous strain. That's the easy test, right?
Yeah.
The whole point of this is the mismatch problem. Did it work against a different flu?
That's the million-dollar question. And they challenged the mice with H3N2, a completely different subtype, and also the 2009 pandemic H1N1 strain. And remember, the nucleoprotein they used for the vaccine was based on a strain from 1933.
Wow. So you're talking about nearly a century of viral evolution between the vaccine and the virus.
Exactly. And yet, the survival rate for the OVX836 group was 100%.
100% survival against a mismatched virus from a totally different family. That is, well, honestly, that's hard to believe given how fragile our current protection is.
It is impressive. But we need to be very nuanced here about what survival means in this context. And this brings us back to the mechanism. Remember, T cells don't block the door. They clear the room.
Right.
The mice survived, yes.
Yeah.
But they did lose weight.
They lost weight.
Yes. In mouse models, weight loss is the primary proxy for sickness. The vaccinated mice got sick, the virus entered, it began to replicate, and the mice lost weight. But then the T cells kicked in, cleared the virus, and they recovered rapidly. The control mice they lost weight and kept losing it until they died.
Yeah. So this isn't a force field. You might still have a rough couple of days, but you stay out of the morgue.
Exactly. It turns a lethal infection into a manageable one. It provides clinical protection, not sterilizing immunity.
That distinction is huge. I think a lot of people expect a vaccine to mean I won't catch it. This is more like you might catch it, but it won't wreck you.
Which, if you think about a pandemic scenario, is the difference between a global catastrophe and a heavy flu season. If everyone gets sick but recovers in 3 days, society keeps functioning.
True. But nobody wants to get sick. So is the goal here to replace the flu shot, or is there a better way?
The researchers actually propose a combo strategy.
Ah, why choose one when you can have both?
Precisely. They tested giving OVX836 alongside the standard seasonal flu shot. And this is where the news gets really good. There was no interference. Sometimes vaccines can cancel each other out or compete for the immune system's attention, but these two, they worked in synergy.
So you get the antibodies to try and block the door, and the T cells are waiting in the hallway just in case.
And the data showed this combination led to the greatest reduction in viral load in the lungs. It's a layered defense. You use the standard shot to gamble on a total block. If the scientists guessed right, great, you don't get sick at all. But if they guessed wrong, or if the virus drifts, which we know it does, OVX836 acts as the ultimate safety net to prevent a severe outcome.
That sounds like a much, much smarter insurance policy.
It is. But there's also a deeper, maybe slightly controversial point raised in the discussion of the paper. They note that our current reliance on seasonal vaccines might be a double-edged sword.
How so?
Well, think about how immunity works. You get strong T-cell immunity by actually fighting off the virus, by letting it get inside and having your body learn the internal structure. If we are constantly trying to block the infection completely with antibodies from the seasonal shot, we might be preventing people from developing that natural, broad T-cell immunity.
So by shielding ourselves so effectively from the infection, we're actually keeping our bodies naive to the guts of the virus.
Potentially. We might be making ourselves uniquely vulnerable to a pandemic strain because we never let our bodies see the internal machinery of the virus. We rely entirely on the code.
That's unsettling. It's like we're building a wall, but we fired all the internal security guards. If the wall gets breached, we're helpless.
That's a great way to put it.
Yeah.
And that's why a vaccine like OVX836 is so critical. It could artificially provide that natural-style, broad immunity training the internal security guards without us having to suffer through the actual illness to get it. It mimics the benefits of infection without the risk of death.
So zooming out, what's the takeaway for the listener? Are we looking at the end of the flu season as we know it?
I think we're looking at a potential universal vaccine component.
Okay.
It's a move toward baseline protection. Imagine a world where even if a brand new H5N1 or some other scary avian flu jumps to humans, something we've never seen before, your immune system already recognizes the internal architecture because of a shot you got 3 years ago.
It removes the panic.
It lowers the stakes. It turns an existential threat into a manageable illness.
I just want to go back to the heptamer thing one last time, the spider. It really highlights that biology isn't just chemistry, is it? It's physics, it's shape.
That is the provocative thought I'm left with from this paper. If we can engineer proteins to form specific geometries, like these heptamers, to trick the immune system into paying attention, what else have we been ignoring?
You mean for other diseases?
Exactly. Cancer antigens, other chronic viral infections like HIV or hepatitis C. So often the problem is that the immune system just doesn't see the threat clearly. The antigens are too weak or too boring. If we can change the shape of the antigen to make it impossible to ignore, if we can package it in a way that dendritic cells just love, we might be able to wake up the body's defenses against things we currently consider incurable.
So it's not just about finding the right drug, it's about presenting it in the right package.
The geometry of medicine. It's a whole new frontier.
Well, next time I'm waiting in line at the pharmacy, I'm not just going to be thinking about antibodies and hoping the scientists guessed right. I'm going to be hoping for a 7-headed protein spider to back them up.
A smarter mousetrap.
Exactly. Thanks for guiding us through the complexities today. It's really rare to find a paper that offers this much hope with this much hard science behind it.
My pleasure.
And to you listening, keep an eye on OVX836. The name might not roll off the tongue, but it might just save your life one day. Stay curious.